All right, so module 8.2, graphing more complicated rational functions. We're going to talk about asymptotes versus wholes. So we've talked about a constant over linear, 1 over x. We have talked about a linear over linear, so 3x minus 4 over x plus 1. We are now going to move into some other types of rational functions. So linear over quadratic, a quadratic over a linear, and a quadratic over a quadratic. So these are the things we're going to be discussing. Here in green, and I'm really hoping you guys can see this, when dealing with quadratics, we must factor first. That's a key thing. Values that blow up our denominator are generally vertical asymptotes, but when the factors in the denominator cancel with a factor in the numerator, we've got a whole. If the degree of the numerator is less than the degree of the denominator, which means you have maybe a linear over quadratic, and it's a degree less by 1, then y equals 0 is the horizontal asymptote. If the power of the numerator and the denominator are the same, then we can find that horizontal asymptote as y equals a over b. We can also use dividing to help us with that. And then moving onward, if the power of the numerator is 1 degree higher than the denominator, then we have a slant asymptote. So that might be where we have the quadratic over the linear. And we're going to find that by dividing. So we're going to start off, we're going to sketch the graph of the given rational function, find asymptotes and wholes, state the function's domain and range. So this is the first function we're looking at. This is a linear over a linear. And the first thing we're going to do is identify. We have a vertical asymptote with what blows up the denominator. So here, if I plug this in and I say, okay, x minus 2, what makes that equal to 0? Well, x equals 2, and that becomes my vertical asymptote. It means that that's kind of like a black hole, can't cross it, falls into the abyss. Because there's nothing canceling in the numerator and denominator, the wholes, there are none. That only happens when we have a cancellation. The powers are the same, power of 1 and 1. So we're going to figure out what the horizontal asymptote is by taking our a value over our b value. So in this case, the number in front of the x is 1, the number in front of the other x in the denominator is 1. So my horizontal asymptote, y equals 1 over 1. That's a over b, so that's just 1. So y equals 1 becomes our horizontal asymptote. So we need to look at maybe graphing this. We can figure out what x-intercepts look like and talk about domain and range. But first of all, let's get our asymptotes drawn on our graph. So I'm going to slide this board down. And this tells me I have a vertical asymptote at x equals 2. So let's do that in maybe green. So when x is 2, there is my vertical asymptote. And I have another one when y equals 1. That is my horizontal. And it's shifting my graph. So x-intercept is when the value is equal to 0. We can look at this. I can rewrite this and say, all right, x minus, that's x plus 1. I can divide it in. That goes in 1 time. That's x minus 2. Change your signs. That's a positive 3. So I can rewrite that as 3 over x minus 2 plus 1. That's another way of getting your asymptotes. Now, looking at this, you can figure out what the x-intercept is by saying x plus 1 equals 0. Look at that numerator. And in that case, when x is equal to negative 1. So when x is negative 1, that's where that intercept is happening. Now, we're going to graph. And here. And here. My a value is positive, therefore my quadrant is, or my graphs are in quadrants 1 and 3. There we go. So, talking about domain and range. So, listing out your domain and your range. The domain, we have 2 parts. So, we have the part that's to the left of 2, and we have the part that's to the right of 2. So the domain, it can be, say, x, such that x is less than 2, or x is greater than 2, because x cannot equal 2. And if we write that in interval notation, we can simply say negative infinity, because it's going to go continue forever to the negative, comma 2, and then it's going to be combined with positive 2 to positive infinity. So it's starting at 2 and going this way. This parenthesis means it's not including 2. The range, well, let's look at it. It's doing the same thing. It can't hit 1, so that means the range, and I can rewrite that as y such that y is either less than 1 or it's greater than 1. And you do the same thing for your interval notation. It's going to go negative infinity to positive 1, combined with 1 to positive infinity. Now, we have another problem I want to look at, and it's going to be way over here. Turn you guys this way just a little. This is a quadratic over a linear. So looking at our information, when the power of the numerator is 1 degree higher than the denominator, we have a slant asymptote, and we have to find that by dividing. So we're going to get to dividing, but before we start dividing, we really do need to factor. So this numerator factors to x plus 2, x minus 1 over x plus 3. Nothing cancels out, which means we have no wholes. So wholes, none. Let's talk about a vertical asymptote. Well, the vertical asymptote is what blows up the denominator. So what value of x would make this be 0? Think to yourself, x plus 3 can't equal 0, so that means x cannot equal negative 3. So my vertical asymptote is at x equals negative 3. It's where things fall apart. The horizontal asymptote, power is bigger, so we have to divide to find it. X plus 3, and we're going to divide into x squared plus x minus 2. So we have an x. That gives me x squared plus 3x, because we're distributing this to here. Change your signs. Those cancel. We get a negative 2x minus 2. And then we have a minus 2. And distribute that. So we get negative 2x minus 6. Change the signs. That's 4. So now, this right here, that is our slant asymptote. So our slant asymptote is the equation y equals x minus 2. So we're going to look at graphing, and I'm going to draw in the asymptotes. I don't have any holes to worry about. X equals negative 3. There's that vertical line. And then here, y equals x minus 2. The intercept is at negative 2. It's up 1 and over 1, up 1 over 1. We can go down and over, and down and over. So we get this dotted line. That's called a slant asymptote. And we are pretty much set to graph now. So looking at this, we need to figure out where our intercepts are. So looking at the numerator, where is it going to cross x-axis? When x is 0, it's going to cross either at negative 2 or at positive 1. So when y is 0, it's going to cross at negative 2, and it's going to cross at positive 1. It's going to kind of make a little bend. So our graph is going to come down, and it's going to loop back out, and then it's going to do the same thing down here. Loop back out. We know these have to be curved. Rational functions are not straight lines. They're not linear. They are going to be curved. Now, if I have time to do one more, where we have the numerator, small denominator, same thing. If I have the function f of x equals x plus 1 over x squared plus 3x minus 4, if we factor this, we get this value. No holes again, but we have two vertical asymptotes. So you get a section of a graph. Let's see if I can move you guys way over here, because I need to do this quickly. It's going to have a vertical asymptote here and one over here. So we're going to have a piece of graph going like this, down and changing, and here. You need to find your intercepts where it's crossing, but this is what it looks like, and because this is going to cut me off, we'll talk more about this later.